Good morning, everybody. Let's start this session in a short while. Waiting for some more people to join. You're just 33 members. Okay. One more request is if you are into video, if you are in video mode, just switch off your video so that we can save that extra bandwidth that is being used for the video. I'm also going off the video and only my audio will be on for you. This is just to save the bandwidth and to make the signal good for other resources. Okay. Today we shall start with solving some problems. That means finding the Z transforms for some signals that we already have seen. Okay. So you need to be ready with your books and pen so that it's as good as solving problems in the class. Okay. So you need to be ready with your pen and paper or book. Okay, I hope you're all maintaining the same notes that you used to bring to the class. Okay, so you continue in the same notes. Yeah, so let's go with the actual content. Yeah, so this is what I'm going with today. Just transforms of some useful sequences. Till now, we have seen the Z transform of the finite sequences, infinite sequences. Some of those sequences are again going to be repeated here. Okay, if such signals come, I'll not be doing the whole transform operation. Okay, I'll just be recalling whatever we have done earlier. Okay, so let's see which is the signal that we're going to take first. Okay, the first sequence that we are taking is unit impulse function. What is unit impulse function? Remember that delta of t in continuous time, delta of n in discrete time. In delta of t is continuous in time and its amplitude is uh, unbounded at t equal to 0 in continuous time. But in discrete time, delta of n is equal to 1 at n equal to 0. This is the main difference that one needs to understand. Okay, so here we have a sample of amplitude 1 at n equal to 0. That is your unit impulse function. That is delta of n. What is delta of n? Delta of n is 1 at n equal to 0 and it is 0 at all n not equal to 0. So there is a signal existing only at n equal to 1. Okay, now we need to find the Z transform of this delta of n. The formula is same. X of z is given by the summation of x of n into z to the power minus n, where n is running from minus infinity to plus infinity. Fine. Now we have to substitute the delta of n in place of x of n in our next step. This is how it looks like. Now, how to solve this summation? Now to solve this summation, we need to recall the property of delta of n we have seen. Okay, property of delta of n needs to be recalled. Fine. So what is that property of delta of t or delta of n that we need to remember? Okay, so here shifting property of delta of n. How does it look like? See here, summation x of n delta of n if you have. Okay, then this summation of x of n into delta of n is given by x of n at n equal to 0. X of n being evaluated at n. Why x of n is being evaluated at n equal to 0? Because delta of n exists at n equal to 0. So this whole summation is actually x of n being evaluated at n where this exists. This is the shifting property of delta of n. Okay, so this whole stuff can be written as this can be written as x of 0. Now how do you relate this particular summation to this standard summation that we have in shifting property? Now
See, delta of n is anywhere there. Okay, so along with delta of n, we need to have x of n. So this z to the power of minus n forms x of n. Okay, so here x of n is being evaluated at n equal to 0. That means here z to the power of minus n needs to be evaluated at n equal to 0. That is what one needs to understand. Everybody's okay with that? So we are so maybe there are some people who are not aware of what is shifting property. When we discussed the basic signals, okay, delta of t, delta of n, we came across the properties of the delta function or the unit impulse function. Unit impulse function is also called as delta function because it is represented by delta. Understand that? So it's also called as delta function. In the properties of delta function, there is one of the properties which is called as shifting property, and it says this. Okay, so because of this property, in this summation, we will be evaluating this z to the power of minus n, which forms x of n actually. Okay, so this will be evaluating at n equal to 0. We evaluate this at n equal to 0 because delta of n is existing only at n equal to 0. That's why this can be seen as this summation can be seen as z to the power of minus n being evaluated at n equal to 0. Understand that? So when we evaluate it at n equal to 0, it becomes z to the power of minus 0 or z to the power of 0, which is 1. Anything to the power 0 is 1. That's why this the z transform of delta of n is happening to be 1. And since it is 1, the ROC is entire z plane, all the values of z. It's not that we are except z equal to 0 or except z equal. No, we don't say all that at all. All the values of z would form the region of convergence for the z transform of delta of n. Understand? So if you have a unit impulse function, the z transform of unit impulse function is unity, okay, and ROC is all z as it says. Remember this. Okay, so this is one version of delta of n we are seeing. We can even have the shifted versions of delta of n. Understand that? We can even have shifted versions of delta of n. What is that? See here? This is shifted version of delta of n. Where is this shifted? Delta of n exists at n equal to 0. So that means delta of n minus n naught exists where? On the right hand side or on the left hand side of n equal to 0. It exists at right hand side. That's why delta of n minus n naught exists at n equal to n naught. Remember, this delta of n exists at n equal to 0. Delta of n minus n naught exists at n equal to n naught. Okay, so see here, now this delta of n minus n naught needs to be brought here. This is how it looks like. Now again by shifting property, you have to evaluate this summation. So how to evaluate this summation from the shifting property? Earlier it was x of n being evaluated at n equal to 0 because delta of n exists at n equal to 0. Now see here, delta of n minus n naught exists at n equal to n naught. That's why this x of n needs to be evaluated at n equal to n naught. What is x of n here? The signal which is along with delta function is x of n. So this needs to be evaluated at n where this delta of n minus n naught exists. Get that point? So what would this summation be? The whole summation would be equal to z to the power minus n being evaluated at n equal to n naught. Okay, so if you evaluate z proof minus n at n equal to n naught, it would become z proof minus n naught. Then how do they say ROC is z greater than 0? How to read this ROC? If you have done your homework or if you have gone through what we have discussed so far, okay, you should be able to understand what is the meaning of ROC being magnitude z greater than 0. What is ROC? First of all, ROC is the values of z for which x of z is finite. So for what values of z x of z is finite? Now this is x of z. So for what values of z x of z would be finite? So this can be represented 1 by z to the power n naught, 1 by z to the power n naught. Now z would come in the denominator. So if z comes in the denominator, okay, if it is 0, x of z would be infinite. So it is not supposed to be 0. So that means except 0, all other values of z would form the ROC. How to represent that? It is represented in this form. Except z equal to 0, okay, minus z's and plus z's and minus z's on z axis would form ROC, but z equal to 0 would not be a part of ROC, is what is the meaning of this. So this needs to be written by seeing this. Okay, if z is 0, this is infinity, so leave that z equal to 0, rest all would become the region of convergence, so which is represented like this, which means a z greater than 0 or minus z less than 0 is the meaning of this. Okay, it's all the same. Now let's go on with another shifted version. This is delta of n minus n naught. Another shifted version would be delta of n plus n naught. Everybody understand that? It is going to be delta of n plus n naught. Now again bring the delta of n plus n naught in place of x of n. See where this delta of n plus n naught exists. This where does it exist? It exists at n equal to minus n naught. Delta of n plus n naught is shifting delta of n to the left by n naught samples. Okay, so it will be shifting delta of n to the left by n naught. So delta of n would be delta of n plus n naught would be existing at n equal to minus n naught. Okay, so how to evaluate this from the shifting property? The shifting property very clearly says if it is n plus n naught, x of n needs to be evaluated at n equal to minus n naught, because this exists at n equal to minus n naught. So x of n would become x of minus n naught. So what would this z to the power of minus n become? So z to the power of minus n at n equal to minus n naught would become z to the power plus n naught. So when z to the power of plus n naught can become infinite, it would become infinite when z equal to infinity. So that is not your ROC. What is ROC? So except z equal to infinity, all other values of z would form ROC. How to represent that? It can be represented like this. All the values of z. So if it is magnitude, you should read it like that. It's all the values of z except z equal to infinity. Understand? So this is what is the first sequence we have seen, that is delta of n sequence. What is it called as? It is called as unit impulse function. So one thing that you should remember here is the shifting property. Understand? It's the shifting property, not the shifting property. Shifting means it's distributing. That means you're picking one among many. Okay, you are picking one among many. There are many such. If this is an example we have taken, yeah, x of n, there could be many samples of x of n at n equal to 0, at n equal to 1, and n equal to 2. Okay, so if you multiply it with this and some take summation of that, you're just taking one sample out of it among the many samples. So that is shifting. Okay, taking one, able to be selecting one sample out of many is what shifting property talks about. Okay, and that happens with this. Fine. Now let's go with the positive time exponential. This is something that we have seen when we were discussing the region of convergence for infinite sequence. Finite sequence also we have seen. This is for infinite sequence. Okay, and again I'm not going to deal with this. This is something that we have found earlier. Okay, that part of the notes is already been put in Google Classroom for your reference. Okay, you can go through that if you're not aware of this. Even the third sequence is something that we have seen, negative time exponential. So if you have to recall how the negative time exponential looks like, if this is positive exponential or positive time exponential, negative time exponential looks like what? Okay, there will be a negative sign. In place of a, they have taken b. So minus b to the power n u of minus n minus 1, because positive time exponential goes from 0 to infinity, negative time exponential goes from minus infinity to minus 1. See here, x of n is minus b to the power n u of minus n minus 1, and we have found that x of z of this is z by z minus b. Okay, and ROC would be less than b, less than b. See, what does that mean? Here, z greater than a means here a also has got the magnitude. Here a also has got the magnitude means you should understand that z is z. Here it's a positive time exponential, and the ROC is outside the circle of radius a. Is the meaning of this. For positive time exponential, region of convergence is outside the circle with radius a. For negative time exponential, ROC is inside the circle with radius b. It's inside the circle with radius b. It's outside the circle with radius b. And if it is a unit step function, if it is both sided, double sided exponential, then it's a ring. That also we have seen. It's a ring. If it is sorry, double sided exponential sequence, which ranges from minus infinity to plus infinity. Understand that? Now let's go on with the fourth one, that is unit step sequence. What is the notation for unit step sequence? How the unit step sequence is denoted? The unit impulse function is denoted as delta of n. The unit step sequence is denoted as u of n. Understand that? It is denoted as u of n. See, this is how it looks like. Okay, if x of n is u of n, okay, how do you when so in our previous example we have seen what is the z transform of a of n u of n, right? So that is this. The z transform of a power n u of n is z by z minus a, whose ROC is outside the circle with radius a. Now, seeing this, can you tell the z transform of u of n is the question. Listen to me again. This is something that we have derived already. Now, with this result, is it possible to obtain the z transform of this? Z transform of a of n, a power n u of n is z by z minus a. Okay. Now, if it is z by z minus a by a power n u of n, what is it for u of n? So, seeing this, you should be able to see it. Now, how to do that? When can a power n u of n be u of n? This is the question. When can a power n u of n can be u of n? In other words, when can our positive time exponential, when can our positive time exponential be just the unit step function? Okay, so that is the idea. Fine. Just a sec. I'll do some setting and come back. I'm stopping the share for a while. Just be there. Yes. Just a second. I'm coming back. Yeah. Yeah. Fine. So when can a when can a power n u of n be u of n? A power n u of n can be u of n when this a is equal to 1. Everybody understand that? when this a is equal to 1, u of a par u of n can become u of n. Everybody is okay with that? Here, when this a is 1, substitute a is equal to 1 here, so it becomes 1 par n. 1 power anything is 1. Okay, so this whole stuff become u of n. So when a is becoming 1 here, this a should also become 1, and in the ROC, this a should also become 1, is what we need to understand. So that is what we talk about in the next step. Assuming a equal to 1. In this, assuming a equal to 1, we can write z transform of u of n is z by z minus 1, and ROC being z greater than 1, which means that ROC is outside the circle with radius 1. Region of convergence is outside the circle with radius 1. Here the region of convergence was outside the circle with radius a, but now a is 1 here in u of n. Okay, that's why region of convergence is outside the circle with radius 1. Is the meaning of this. So how did we find the Z transform of unit step sequence? We found out the Z transform of unit step sequence from the Z transform of positive time exponential. Is that okay from with you? Okay, then let's go with the next sequence. Okay, that's negative time unit step sequence. As we found out the unit steps sequence, Z transform unit step sequence from positive time exponential, let's find out the negative time unit step sequence from the Z transform of this from negative time exponential. So it looks like this. X of n is minus u of minus n minus 1 is negative time unit step sequence. This we had not seen. We know u of n. We were very much aware of u of n. What if u of n is minus u of minus n minus 1? Then it is called as negative time unit step sequence. How to obtain the Z transform of this? The Z transform of this can be obtained from understanding the Z transform of the negative time exponential. So when can this negative time exponential be negative time unit step sequence? It can be negative time unit step sequence if b is equal to 1. So if b is equal to 1, it becomes this. So when b is equal to 1, the Z transform of this is z by z minus b, with region of convergence being inside the circle with z less than 1. That means inside the circle with z equal to b circle. That means you draw a circle with radius b. Okay, so within that circle is what is the region of convergence of this. So what is the region of convergence of this? The region of convergence of this is inside the circle with radius 1, because b is 1 here. That is what is told. Assuming b equal to 1, we get z transform of this as z transform of this as z by z minus 1, with ROC being within the circle of radius 1. Yes, so this is negative time step unit step sequence. Sinusoidal sequence. Now we have seen how sinusoidal sequence looks like in discrete time. How does it look in discrete time? Yeah, anybody? How does the sinusoidal sequence in discrete time looks like? Yeah. See here? This W omega is not used. Instead, we use this ohm omega. Ohm omega is not the proper terminology, but to differentiate between the continuous time ohm and discrete time ohm, we are using. I mean, just call this as ohm omega naught into n. Sine omega naught into n would be the sinusoidal sequence, and the sinusoidal sequence exists ranges from 0 to infinity. Who tells that the sinusoidal sequence exists from 0 to infinity? This particular u of n tells that this function of n exists from 0 to infinity. Okay, so if you have to find the z transform of this, you need to substitute this sinusoidal function in place of x of n. That is what is done in the next step. Now, what needs to be done in this step, everybody? This is something that we are being doing with every sequence when we are finding the Z transform. We manipulate the what? The limits of summation. The range of summation. From where to where we are going as of now? As of now, we are going from minus infinity to plus infinity. But you all know from where to where u of n exists. U of n exists from 0 to infinity. So there is no point summing up from minus infinity to minus 1. So change this summation range from 0 to infinity and just make this u of n 1 in that range. So that is what is done in the next step. Okay, and finding the summation of the sinusoidal as it is would be difficult task. So what do? We express this sinusoidal in terms of the complex exponential. Can anybody recall and write that on paper? What is the sinus? What is the complex exponential form of sine omega naught n? How can we express the sine omega naught n in terms of complex exponential? It is e power j omega naught n minus e power minus j omega naught n divided by. Remember that? Here I have that equation for you. See, this is the equation. Sine omega naught can be expressed in complex exponential form like this. Okay. In the denominator, okay, we have 2j. It's not just 2, but it's 2j. If it is cos omega naught n, the cos omega naught n means it is e power j omega naught n plus e power minus j omega naught divided by 2. But in sine omega naught n, we'll be having a minus here and we'll be having an additional j along with 2 in the denominator. Okay, now this complex exponential form needs to be substituted in place of sine omega naught n, and after we do that, the equation comes to this form. Fine. Now we need to take uh, one thing out of the summation. Which one thing is that which can be taken out of the summation? See, which is not the function of n. See, this summation is running from 0 to infinity, right? Okay, so what is not a function of n here? This is a function of n, this is a function of n, this is a function of n, but this is not the function of n. Keep this out. So this is a constant now. Keep this out of summation and deal with the rest of the part. Okay, this is how it can be done. What is done here? So 1 by 2j is kept outside. This summation is now being applied to this exponential along with z to the power minus n. Similarly, this summation is also applied to the second complex exponential along with this z to the power minus n. But understand, there is in the power, there is n common. Okay, in the power, there is n common. Understand that? So what would happen? Take that n common out from the power. Okay, the exponential along with z would look like this and this. Yes. Now, is this in the standard form of summation? Is the question. Yes, this is in the standard form of the summation. In place of this, if we have a, what would happen? Summation n ranging from 0 to infinity a par n. What would happen? It would be 1 by 1 minus a, right? Similarly, this summation would be 1 by 1 minus e par j omega naught into j z inverse. Similarly, this would be 1 by 1 minus e par minus j omega naught into z inverse. So that is what is written here. Everybody is okay with this. So this is the standard form which we have seen so many times. Okay, I'm not told how did we write this. Maybe at that standard summation I'll write here when I provide these slides to you. Fine. That's so because of the standard summation we are able to write like this. Okay, so soon after you solve your summation, the result of summation where you get, that is where you'll be evaluating your region of convergence. So at this stage we need to evaluate. So this needs to be further simplified. Okay, this particular result x of z needs to be further simplified. But before going with the simplification of the result, let's understand how to find out the region of convergence at this point of time. Every time I've been telling, whenever you find x of z, we need to find out ROC. And when you find ROC in the solution, you'll find the ROC when you get the result of the summation. Okay, so soon after you get the result of summation, there itself you try get your region of convergence. So what is region of convergence? Region of convergence is values of z for which x of z is finite. So for this to be finite, the denominators should not be 0, because 1 by 0 would make it infinite. 1 by 0 here would make it infinite. So the denominator should not be equal to 0. So how can that be taken care of? That can be taken care of by taking the magnitude of this denominator greater than 0. So magnitude of this denominator taken as greater than 0. That is what is this. Let's just understand how they have calculated region of convergence. Okay, see here, the denominator is taken. The magnitude of denominator has to be greater than 0 for this not to be infinite. Okay, so if this is infinite, that will not be a part of ROC. So except that, okay, so except that the magnitude of this is going to be ROC. So if we say 1 minus e power j omega naught into z inverse is greater than 0, then it is as good as saying 1 is greater than this particular parameter. That means the 1 would be on the left hand side. This minus this would come on right hand side. This is how the equation is going to look like. Now if there are two parameters, okay, so we can make that two parameters look like this separately. Magnitude of this as well as magnitude of this. And we should understand magnitude of any complex exponential is 1. This is an advantage, everybody understanding that. Okay, magnitude of the complex exponential is 1. How can we express this e power j omega naught in terms of the sinusoidals? It is sine omega naught plus j, sorry, it is cos omega naught. This is cos omega naught plus j sin omega naught. Cos omega naught plus j sin omega naught. What is the magnitude of cos omega naught plus j sin omega naught? The magnitude of cos omega naught plus j sin omega naught is square root of cos square omega naught plus sin square omega naught. We know that cos square theta plus sin square theta is 1, and square root of 1 would always be 1. So because of that, the magnitude of this complex exponential is 1. Okay, so if this is substituted as 1, what is left behind is 1 greater than the magnitude of z inverse. So if we take this z inverse as 1 by z, this reduces to z greater than 1. So that is the ROC. What is ROC now? ROC is outside z equal to 1 circle. Similarly, what is going to be the ROC that we can find out from this? Same expressions. Instead of the positive power of exponential, we have taken negative power exponential. Okay, so the whether it is positive power of exponential or negative power of this complex exponential, the magnitude is anyways is going to be 1. So the same result would happen. So you can see from both the terms we're able to find the same ROC, that is z greater than 1. So that is what is going to be the ROC of x of z. Okay, so how did we obtain this? So we have obtained ROs here. From here, we are trying to simplify this stuff. So we are trying to express this in terms of z. How to do that? Take this z as 1 by z. Take the LCM, so it would be z minus this exponential divided by z. Take that z to the numerator. So it looks like this. Okay. Now, if you take the what LCM and multiply, this is how it is going to look like. So z plus z square minus z square, it will go off, and you're left with here e power j omega naught minus e power minus j omega naught. Yeah. So if you take z common, you have plus z, you have minus z. So it's e power j omega naught minus e power minus j omega naught. Okay, in the denominator, what would be left behind? You have z square, and this minus z you take common, you'll be left with e power j omega naught plus e power minus j omega naught plus 1. Is there any way out in which you can express these exponentials in terms of sinusoidals? Is there any way out here? What is this divided by 2j? What is this divided by 2j? So divided by 2j is sine omega naught. Okay, here this divided by 2j sine omega. So in this place, so this 2j can be taken here in the denominator here. This whole stuff along with this in the denominator would become sine omega naught. Okay, so that is one part. How can we discuss? How can we express this? E power j naught plus e power minus j naught divided by 2 would be cos omega naught. So it is just only this part is there. So this part can be written as 2 into cos omega naught. So that is what is done here. Okay, so this is what is the x of z, and this is what is the region of convergence that we have found out in few steps back. Fine. On similar grounds, we can find out the z transform of cos omega naught in also. So this I've given you for assignment. I'm not doing this. If you have textbooks, you'll find that, but I don't advise you to go through the textbooks for this, because we have seen what is sin omega naught in detail. On the same grounds, you find out the z transform of cos omega naught n. The answer has been given here, and the region of convergence would also be equal to z greater than combined to z greater than 1. So take this as an assignment. Solve this in the assignment book that you have with you, along with whatever I've given you till now. Solve this also. Maybe when you meet in the college or somewhere in between, I may ask some people to scan your book and submit your assignment online. Okay, so with that, we'll stop this class. Now I request everybody to give your attendance. We have 1.5 minutes left. Okay, I request everybody to give your attendance in chat window. Yeah, good. We are 47 participants. I hope all 47 participants have given that. It's less than a minute now, so hurry up. And if you have any problems, post your problems on Google Classroom. Okay, I'm not seeing that in last 2 days. I'll be seeing that today. Fine. If you have anything to be asked, anything that you have not understood, put your questions there. Okay, I'll be answering that shortly. Fine. Yes. I hope everybody has given your attendance. Now let's stop this session. Okay. Thanks. Thanks. Take care, everybody.